Okay, welcome back. Before we have been talking about two different hash tables, right? We analyze its performance as well as its potential problems. For the conventional hash table, we say it's very efficient. However, if we have so many overflow blocks, its running performance will be degraded greatly because it will reduce the hash table to just a linear list, right? And its search process can be very time costly. So therefore we have to introduce another hash table. It's called extensible hash table, right? In extensible hash table, we can grow the hash table, both the buckets as well as the hash function, in a vertical way by including more bits or digits into defining both the hash function as well as the buckets. It allows us to grow the hash table in a vertical way instead of the horizontal way, right? It can ensure the hash function can always be efficient and effective during the running time. However, we will find some problems with the extensible hash table. Remember before, right? We mentioned we can grow both the hash function as well as the buckets by increasing the number of bits used for defining them. Then it can create some problems. Even though right now this extensible hash table they don't have any overflow blocks, right? And we can always access the corresponding entry via one read of this hash function. However, its extension in the extensible hash table can be very costly or disruptive. Because during the running time, if we insert one key into the hash table, we have to grow the hash table. And this growing process can be costly in both time and as well as space. Also, this growth in this extensible hash table can be dramatic, because we grow the hash table by increasing its bits, right? In other words, whenever we grow it, we will double its size, right? If we grow this I from 1 to 2, we have to double the size of the hash function as well as the buckets. Whenever we grow the hash table, we almost double its size. You know, if we double size for every growth, then the growing potential or capacity for the hash table will be very limited, right? Because it will grow very fast in the storage space. Therefore, for both of these two hash tables, they all have their shortcomings in their performance. So for the first one, this conventional hash table will grow it in the horizontal way. It can create some problems. For the second one, if we grow the vertical way, it can also create some problems. And we may wonder if we have any other options or not. The answer is yes, we can have another option. It's called linear hash table. So linear hash table allows us to grow the hash table during the running time in both horizontal way as well as the vertical way. It combines advantages from both the conventional hash table with this extensible hash table. The idea for the linear hash table is to grow this hash table by only creating one entry at a time. Before we mentioned that for the conventional hash table, we can grow it by creating one bucket at a time. However, for this one, we can grow it by doubling its size at each time of the growth. It would be a very bad option, right? Therefore, we plan to use the advantage from the conventional hash table by growing it one bucket at a time. And we also have some problems, because for this linear hash table, we cannot guarantee that the n, or the number of buckets, will be a power of 2 anymore during the running time. The linear hash table is combined both the conventional hash table with this extended hash table. It is also defining this hash function based on the bits in the input keys. However, here we use I bits. For the linear hash table, we still use I bits for defining the hash function. However, the number of buckets we have for this hash table will be no longer a power of 2 anymore. Let's assume we use the I bits to be used for defining the hash function, and the number of buckets we can create based on the first I bits will be in a range from 2 to raised to the I minus 1 and 2 to the I. You can see the difference, right? So before we mentioned that for the extended hash table, we use the first I bits for defining the hash function and with the buckets. We can guarantee, right, the number of buckets will be equal to 2 raised to I. If we only use 1 bits, the buckets we have will be 2, right? If we use 2 bits, then the buckets we can have will be 4, right? However, for this linear hash table, we guarantee that we only grow 1 entry or 1 bucket at a time. In other words, we cannot guarantee this n equals 2 some power of 2 anymore. It will be in the range from 2 to the I minus 1 to 2 to the I. So you can see the difference, right? We don't need to double its size every time. In other words, this n will be no greater than 2 to the I. It will be much smaller than 2 to the I actually in the real world. Another difference here is in the hash function definition. Before we mentioned that we use the first I bits for define hash function, right? However, here for the linear hash table, we decide to use the last I bits instead. We use the last I bits for define hash function to represent a number which is no smaller than n. And we can also change the most important or significant bits from 1 to 0. Also, if the last I bits represent a number which is greater than n, in other words, it exceeds right now the bucket numbers, we can even change the most important bits from 1 to 0. And if we change this, we need to guarantee this number is smaller than n. So this is the linear hash table. I can provide you with some concrete examples to help you understand what we mentioned here for defined linear hash tables.